Okay, so hello and welcome back. In this video, what I want to show you is how a high-pass filter, basically how a high-pass filter works, and basically we will do a couple of experiments on the oscilloscope, and then we will read some values on the oscilloscope. We will measure a few things, voltages and currents and things like that, and then we will do some calculations to bring the whole thing together. So that's basically what we want to do. So basically you are going to learn almost everything there is about, the basic things about a high-pass filter. So now, in order to, first we need to have some sort of circuit diagram in order to know what a high-pass filter is and what it does, and then we will go to the rest of the story. Okay, so I'll bring you down here, and let's get okay, so basically a high-pass filter is also called an RC series circuit, and also a high-pass filter. I'm going to tell you why it's called a high-pass filter. So basically a high-pass filter is some sort of filter that you have. So for example, you could have this, you could have a capacitor over here, and this your input voltage is usually some sort of sinusoidal signal comes in here, and here you have a capacitor, and then you have some sort of resistor. You have some sort of resistor that you can ignore these things, that this resistor goes to ground. This is an R, and then the output voltage is basically, this becomes your V of out. Okay, so you usually use this kind of circuit as a substitute for, this circuit can be used as a substitute for a voltage divider circuit, but of course you know that over here your input is an AC signal. Is an alternating current, or is an AC signal, and over here you will have some AC signal over here, but usually based on the frequency and based on the value of your capacitor and resistor, this output voltage is going to be smaller in magnitude than the input voltage over here. So, and usually what we do in DC circuits, what we do is that, for example, you could have two resistors over here, and these two resistors are connected to a power supply. So this becomes your V of S, and this becomes R1, for example, and R2, and then this becomes a voltage divider circuit. So you will have some voltage is dropped across this resistor over here depending on the value of the resistor. So that becomes V of R1, and this becomes, for example, V of R2. And that way sometimes if you have some sort of power supply, for example, over here 8 volts, and you want to get only half of that voltage, then you install, for example, 2 resistors over here of the same value, for example 2 1 kilo ohm resistors, and then the 2 resistors are going to divide the voltage for you in half. Then you would have 4 volts voltage drop across this resistor and 4 volts across this resistor, and that, for the same reason, it's been called a voltage divider circuit. Now this over here, that your power supply is DC here, but over here your power supply is AC. So now what happens in this circuit is that of course is that you are practically basically measuring the voltage across this resistor here. So this is V of out, and then you're measuring that voltage with respect to ground. So you're actually measuring the voltage drop across the resistor here. And what happens in this circuit is that you have your V of in here, and then this voltage goes to ground. Of course, this current, there's a current that goes to ground, and there is some voltage drop across this capacitor, there is some voltage drop across this resistor, and then you have to basically choose the value of C, choose the value of R, and choose the frequency, the input frequency over here, in such a way that you have the voltage that you want, or the signal that you want at the output, and that's basically why it's called a filter. So what happens is that, as you know, that basically the reactance of this capacitor, X of C, is equal to 1 over 2 pi Fc, 1 over 2 pi Fc, and that the unit of this, you're going to get that in ohms. That means that this that means that this excuse me, that means that this capacitor is going to act like a resistor in this circuit, and that resistance is, in this AC circuit, is called reactance. And this way you can calculate that reactance. And so of course there is some resistance inherently built into this resistor, and so that way you can build your voltage divider circuit. But now what happens here is that when you as you increase your frequency over here, as you increase the input frequency over here, as the frequency goes up, the reactance comes down, because this is in the denominator, this is in the numerator, right? So as you increase the frequency over here, the reactance of this capacitor is decreasing, and the reactance is just some sort of resistance to electric current over here. So the resistance decreasing, that means that the voltage drop across this capacitor is decreasing. So when the voltage drop across this capacitor is decreasing, that means that the rest of the voltage is being dropped across this resistor, and that is your V of out, right? So what happens is that then you will have basically, if this is F of input frequency, and if this is your V of out, as you're increasing the frequency, the reactance of this capacitor is going to decrease. The reactance here is decreasing, and with the decrease in the reactance of this capacitor, the voltage drop across the capacitor is decreasing, and the voltage drop across this resistor is increasing. So that means that the more that you increase your frequency, the voltage drop across the more voltage you're going to have at your output. So that means that you are going to have some sort of graph like this. This is a frequency versus voltage graph for this circuit. Basically, at some point, at some frequency, the voltage across the voltage starts rising, and then at some point it's going to stabilize itself and get very close to the supply voltage. So that's basically how it works. So now let's build one of these circuits and look at the input and output of the circuit on an oscilloscope, and then we will do some calculations and see how basically this circuit behaves. So what I'm going to do is that I'm going to have, so this is a 1 kilo ohm resistor, and this is a 0.01 microfarad capacitor. So you see that the supply voltage comes into this capacitor. So I take this as this is the supply voltage, this is the positive rate, this is the negative rate. So the supply voltage comes in here. Okay, so now one end of this capacitor is connected to the positive supply voltage, although there is no positive negative here. It's an AC circuit, but there is usually the signal and the ground. So I take this as the positive and take this as the negative, for example. And then the other end of the capacitor is connected to the resistor, and then the resistor goes to ground. So I can build this way. So now this resistor is connected to the resistor is connected to the capacitor and goes back to ground. Okay, so that's basically the whole circuit. There is not much to it, although this kind of filter is widely used in radio circuits and all other circuits where you want to basically create some sort of phase shift or change in the phase of the signal, or basically you want to change the amplitude of the signal, and so on and so forth. But in and of itself, it's a simple circuit. Now if I have an oscilloscope up here that I'm going to show in just a second, but this is a signal that is coming in. I don't really know. I know about the frequencies, about 426. We're going to play with that, but this is the positive or the signal itself, and this is the ground. So I connect my signal over here, and then I have two channels on my oscilloscope. This is channel 1. This is channel 1 that I'm going to connect to ground, and then connect to the input, which is this point over here, and then the channel 2 of my oscilloscope I'm going to connect to the output, which is basically the ground goes to ground, and then the output is basically this point where the capacitor is connected to the resistor up here, which is basically any point over here you can take. So I'm going to take, for example, this point over here. Okay. So now if you take a look at this circuit, I'm going to put this away. And if you take a look at your input output okay, if you take a look at your output input on an oscilloscope, first of all I'm going to, let me see what sort of input output I have here. This is channel 1. I'm going to go into alt mode so that I can see both of my signals over here. So this is channel A, channel B, and if I go into alt mode, I'm going to have both of my signals here. So these are both of my signals. This is my input. This is the input signal over here. I put it up here, and this is my output signal channel. Basically, this is my output over here, down here, and this is my input. Now my input is at let's say that it is 3.8 vertical units times 5. 3.8 times 5 is equal to 19 volts peak to peak. So my supply voltage is 19 volts peak to peak, and the other signal that I have, which is my output, is 123.8, again 19 volts peak to peak. So now you see that the output has become almost as much as the input, or exactly as much as the input. And what that means is that the frequency is pretty high over here, because you can of course calculate the frequency over here, or you can read the frequency counter up here. I have connected this output to this frequency counter. You cannot see it, but it's reading 426.972 kilohertz, which means 427 kilohertz. And if you were to calculate the same thing on the oscilloscope, you could basically, if you have a digital oscilloscope, it's going to show you the frequency automatically on your screen, so you have no problem with that. But with these old oscilloscope, with these old oscilloscope, it's not going to calculate much for you. You have to do most of the job for yourself. And I'm going to basically ground channel 1 so that I can center it over here. And I'm going to center this up here, right? And then unground it, and now you see that that channel 1 has been basically centered around this line up here, around this line over here. Bring it a little bit closer here so that you can see. I'm putting more of this. Okay. So now you can see that the input signal is actually grounded. Centered around this line, and to basically calculate the frequency here, you see this is, for example, one complete cycle of this signal. For example, it comes from, if you start from here all the way up to here and all the way up to here, that is one complete cycle. That is the period of your signal. So if you move this around horizontally to, for example, align this point with this junction, you will see that. So you see that over here, 1, 2 point, for example, 2.2, 2.2, basically that's 2.4. We're very close to 2.4. So I take it as 2.38, for example. So that's 2.38, for example. Horizontal units is the period of your input signal. So 2.38 horizontal units times the time base of the oscilloscope, which is right now at 1 microsecond. So you have 1 microsecond. 1 microsecond times 2.38 is your period. Okay, so that's your period, which is basically shown also most of the time by T. I don't know if you can see down here. You can't. So but you could probably see something. I don't know. I cannot move this camera. I cannot move it around so much. So but hopefully you can hear me while I'm explaining this. So 1 microsecond, which was the time based on the oscilloscope, times the number of horizontal units that make up one complete cycle, was 2.38 horizontal units. So that means that the period is basically 2.38 microseconds. That's the period which is denoted by T. Now your frequency is the reciprocal of the period, 1 over T. So that means that your frequency is 1 over 2.38 microseconds, which is equal to 1 over 2.38 into 10 raised to the power negative 6 seconds. Now this is equal to, for example, 10 raised to the power 6 over 2.38, which is equal to 1 into 10 raised to the power 6 over 2.38 gives you 421.68. Gives you 421.68 hertz. And the frequency is hertz, in hertz. And if you read up here on the frequency counter, you have 426.967 kilohertz, right? So 426.9, 427, this is 420. Of course, it's not always easy to read everything very accurately on an oscilloscope, but it gives you some clue as to what sort of frequency you have on your wave. Anyway, so now you have your frequency, and that's basically your input, that's basically your output. Now on this circuit, basically what I showed you was that starting from very small frequencies, the voltage is going to be very low, and this is, by the way, has been called a high pass filter. The reason for that is that at high frequencies much of your signal is passing through, but at very low frequencies much of your signal is being suppressed here, not passing through. So that's basically why it's called a high pass filter, meaning at high frequencies much of your signal is passing through. So now if I play with the frequency here, now I'm at around 400, 1, 2, 3, 4, 5, so that's 423. Oops. Now I'm at 423. That's 4.2 times 100k, which is equal to 4.2 times 100k is equal to 420,000 hertz or 420 kilohertz. So I'm going to bring the frequency down. So for example, to something like this, and then I'm going to, you see over here, now I'm at 43 hertz. I'm at 43 hertz and not much voltage I have on my output. So of course I have to move this up a little bit just for you to see something. But now my output is at about 4 times 20, 80 millivolts or so. That's 80 millivolts, and this is the full supply voltage, which is around 20 volts. This is 20 volts and this is 80 millivolts. Now if I increase the frequency, as you can see, as I increase the frequency, the voltage is going to be rising, as you can see over here. If I increase the frequency, the voltage is going to be rising. Okay, so I'm increasing the frequency from 45 Hertz to 50 Hertz, and now my output voltage is at about the same thing, and now I'm at about, right now I'm at about 50 millivolts times 3 divisions, so 150 millivolts, for example. Right now I'm at about 100 Hertz or so. So I'm going to come over here to 100 and play that with the time base, and you see right now my output is at around 1 to 3 divisions times 0.5 volts, which is 1.5 volts. So right now I'm at around 1 kilohertz. Around 1 kilohertz. So you see, as I decrease the frequency, the output is dropping. As I increase the frequency, the output is increasing. Right now I'm at about 2.5, around 1.5 volts, the output. And as you can see, the input is not changing, right? So I increase the frequency by a factor of 10, and you can see that now my output is at about 1, 2, 3, so it's about 15 volts or so. So right now my frequency is at about so this is 1 volt, so this is around 1.5 volts, and the frequency is about 1,000 hertz or 1 kilohertz. And if I increase the frequency, for example, to 2 kilohertz, you see the output has changed to 3 volts. To 3 kilohertz, the output has changed to I don't know, 4 volts, for example. 4 kilohertz, around the same thing. 5 kilohertz, it's about 5.2, 5.4 volts. Actually more than that. It's about 3 divisions times 2 is equal to about 6 volts. Now if I go to 6 kilohertz, you see it's increasing, and I'm going to decrease this a little bit, move it a little bit higher so I have more space over here. And as you can see, my input is not changing at all, so I'm going to just look at channel B and put it up here for now, and you can see that as I increase, the output is changing, and now I'm at let me see, 1, 2, 3, 4, 5 times 2 equal to around 10 volts peak to peak. If I multiply the frequency by a factor of 10 and go back to 1, and now I'm at about 10 kilohertz, and the output is at 1, 2, 3, 4, 5, or about 10 volts. So about 10 volts here, and I go to about 15 kilohertz. About 15 kilohertz, and as you can see, the output is about 15 volts. 15 volts peak to peak. And 10 times 10, 100 kilohertz. 100 kilohertz, the output is at about 1, 2, 3, 3.8 times 5 is equal to about the input. about the input. So 3.8 times 5 is about 19 volts right now on the input and the output. And if you go some higher than that, and if you go higher than that, now I'm at about 113 kilohertz. Go to I go about 500 kilohertz. 500 kilohertz. You can see that my output is kind of the same thing, because you cannot go any higher than your supply, and your supply is basically this one, which is about this thing over here. So it's about 3.8, and I can put it over here, and you can see that they are exactly the same over here. So your input and output are exactly now the same. So now that's basically what happens with your input and output, and as you saw, you can get different values for your input and output. This is my input, this is my output, this is the bottom one is the output, this is the input. And as you saw, you can get different values for your output depending on the value of the frequency that you can supply to the circuit. Now, for the sake of this experiment, what I want to do is, you can see that right now the two waves, or the two signals, are completely in sync. There is no phase difference between the two. And I want to create some phase difference as well, and that I can do with different frequencies. Different frequencies, I can hopefully get a phase difference, which is right now hasn't happened yet. I think at lower frequencies I can do that. Intensity, then go a little bit higher than that. There is still no phase difference there. I have to go back to very low frequencies, about over here. And now I have the phase difference here. As you can see, the output is this one, which is moving, and now there's a phase difference, and you see the two waves are not actually matching each other. There's a phase difference there. So now this is one of the things that you want to see on your output, and you want to be able to, of course, calculate that as well. So now I'm going to go take a few minutes rest, and then I'll come back. We will note down some numbers from this experiment. I just wanted to show you what's going on with this circuit. Then I'm going to come back, and we will jot down some numbers from this experiment, and then we will get into some calculation. So I'll be back with you just a few moments. Okay, so now what we want to do now is basically connect this thing back. Okay, so now what we want to do now is basically do a couple of measurements, make a couple of measurements, and then use those measurements in order to test our formulas and test our calculation. And of course, measurement is something that you can trust more than calculation, of course, provided that you can trust your test equipment. And well, of course, I can trust this signal generator. It takes of course a whole lot to basically to understand your signal generator or your oscilloscope or other things that you're using are functioning properly, provided that, of course, you buy them second hand. It's always I mean, you will always find something wrong with second hand equipment, but But now I know that this oscilloscope is okay, this signal generator is okay, and the other things that I'm using in this experiment. Okay, so basically now what the parameters that I'm using here are basically my input voltage over here, which is channel 1. This is set to 5 volts per division, and I'm here at so 1, 2, 3, 3.8 division, so that's 19 volts peak to peak. So V of in is equal to 19 volts peak to peak. Now the frequency that, for example, this frequency I suppose is okay for, just to note down, this frequency is 10.676 kilohertz. The frequency is 10.677 kilohertz. Okay, and the other thing that we need is the V of out, which is basically this voltage across the capacitor, across the resistor, which is this voltage. Now the over here I'm set to 5 volts, so this is 2.2 times 5 is equal to 2.2 times 5 is equal to 11 volts peak to peak. V of out, which is equal to actually the same thing as the voltage across the resistor. V of R is equal to 11 volts, and the resistor that I'm using is R is equal to 1 kilo ohm. The capacitor that I'm using is C is equal to 0.01 microfarad, and I think that's all that I need. And there is one thing that I need to measure as well, and that is the voltage across the capacitor, and that's something that I cannot measure using the oscilloscope. And the reason for that is that you see my circuit over here. You see over here, if I want to show you my circuit, so the circuit that I'm working with is actually this capacitor over here that goes to this resistor, and this resistor goes to ground. And this is my V of out, this is V of in, and of course I can use some basically an oscilloscope, and I have basically put my oscilloscope put the oscilloscope probe across these 2 points, and that's actually the output voltage in this circuit. But if I want to measure the voltage across this capacitor, I would have to put basically any sort of oscilloscope probe is basically something like this. So you have a ground lead, and you have the probe itself. So the ground is actually it's actually not possible to do it because the ground in my circuit is over here. Okay, and there are many reasons why you cannot do it. I don't want to make this video any longer than that, but even if you use one channel of your oscilloscope, if you put your ground lead over here, the ground clamp over here, and then want to measure across these 2 points, it's not going to be possible, because then as soon as you connect the ground clip over here, this resistor will be out of circuit. The resistor will be just parked out of the circuit, and for the same reason it's just not possible to do that kind of thing. For example, you could put your ground clip over here and, for example, measure the output voltage over here, the voltage across these 2 points, or you can measure the voltage across these 2 points, or across, for example, these 2 points. You can do. But with an oscilloscope, you cannot go like a multimeter and, for example, take the voltage drop across these 2 points. You cannot do that kind of thing. For that, you need a multimeter. I might sometime in some video get into why that works, or I mean why that is, but for now it's just not possible. So for the voltage across the resistor, what I need to do is just use some sort of, for example, multimeter, but for that you need, of course, you need an RMS multimeter. Not any sort of multimeter is not going to work for you. So I'm going to take this circuit, and I'm going to take this circuit. Let me just see if I can somehow. Okay, so I'm going to take this circuit and use this RMS multimeter up here. I don't know if you can see it. Use this RMS multimeter over here, and basically set it to volts AC, and connect this over here, 8 volts, and then connect and measure the voltage over there. Get rid of these things so you can see something actually. Okay, so now I'm measuring the voltage across the AC voltage across that capacitor, which is 5.31 volts AC. So now I'm going to tell you later what we are going to do with this voltage. Okay, so now the voltage across the capacitor V of C is going to be equal to 5.31 volts, but it's not a peak-to-peak voltage. It's an RMS voltage. It's VRMS. But for example, the V of in that we measured with the oscilloscope over here, this voltage over here that we measured from this peak to this peak, the oscilloscope is showing us the peak-to-peak voltage. But the voltage that this multimeter is showing me, that's the RMS voltage across those 2 points. So you need to be aware of that, so you don't make any wrong assumptions in your circuit. Okay, so that is that. And now I have my V of C, I have my V of out, the frequency, the input voltage. I have the value of the resistor that I'm using in this circuit, the value of the capacitor, and also the current that is going through the circuit. Now, most probably we are not going to be able to use this piece of information, but we will try. Let's see what happens. I don't really know if I can use it. So I set this multimeter to amp. Use it as an amp meter. That's the only good multimeter that I have. The other ones are just, for example, this one is not accurate. I have a couple more multimeters up here, but these ones, for example, I have these 3 ones over here, but these are cheap multimeters that are actually good for nothing. Okay, so this seems to be the only good multimeter that I have. So for now I'm just using this multimeter here. So this is I set this to amps AC, and I go over here and I connect this amp meter in series with my circuit. So if I connect this amp meter in series with the circuit, what I get is 3.85 milliamps. 3.85 milliamps. Okay. 3.85 milliamps. So the current going through the circuit is 3.85 milliamps. Okay, and that is that. Now, one thing that we need, the one last thing that we need here is the phase difference over here. And what this phase difference is, so you see, this is my output voltage right now, this is my input voltage, this is V of in, this is V of out across that resistor. If I bring this up, you see that two waves are kind of displaced. You know, this one, the peak of this one is a little bit to the left, the peak of the other, the peak of basically over here, this is my output, and the peak of that is a little bit to the left of the peak of the one on the top, or the peak of the input one. And what that means is that basically these two have there is some sort of phase difference between these two waveforms. And before I measure the phase difference on this thing over here, I need to tell you a little bit about sinusoidal signals and how they are actually, how the phase difference is actually defined. Otherwise you wouldn't probably, I mean, if you don't know it, you wouldn't probably understand it. Okay, so let's go over a little bit of theory about these sinusoidal signals, and then we will get to the rest of the things that we have. Okay, so in order to understand phase difference, you need to know a couple of things about these I don't know what I did here. Okay, about these sinusoidal signals and these periodic functions. So we are going to talk about specifically about the sine function and the cos function. Okay, and if you, hopefully from trigonometry, you know, at least if you know a simple unit circle, you basically know everything in trigonometry, and then the rest of the things you can just learn along the way. The only thing that in trigonometry that you need to understand is a simple triangle. Okay, a simple triangle like this, a right triangle, and if this angle is theta, then, and this, if I call this ABC triangle, so there are basically two fundamental ratios in any triangle, and that is basically sine and cos. So what that means is that if I denote the length of this side by lowercase c, the length of this side by lowercase b, and the length of this side by lowercase a, then sine of theta is going to, sine of this angle is defined as the opposite side to that angle divided by the length of the hypotenuse, meaning that opposite to hypotenuse, which is equal to c divided by b. Okay, and also the cos of the same angle theta is the same thing as adjacent by hypotenuse. by hypotenuse, which is basically this is the adjacent side A and the hypotenuse is B, so that's A to B. These are two ratios that are going to remain the same no matter how big or small your triangle gets, as long as the angle proportions are kept the same. So now and then based on this you have other functions in trigonometry as well. For example, tan of theta is equal to is by definition is sine theta by cos theta. Okay, so what that means is that sine theta is C by B, and cos theta is A by B, so that's equal to C by A, because B and B will cancel out, and then you have C by A. So that means that the tan of this angle is equal to the opposite side divided by the adjacent side. Okay, so that's basically simple trigonometry in a simple circle. Yeah, in a simple triangle. But the problem is that here this angle cannot be it can be an acute angle, meaning that it can be some angle less than 90 degrees. But if you have larger angles, for example 135 degrees or 120 degrees or something like that, then what mathematicians have done, they have basically moved this triangle into a circle, which they have called a unit circle, and the units in this unit circle is basically built into this coordinate system. You have these lengths, each of which is 1 unit. So this is 1 unit, this is 1 unit, this is 1 unit, this is 1 unit over here. So this is 1, this is -1, this is +1, this is -1. And then you have your circle over here. Okay, you have a circle over here, and you just keep moving around this circle your whole life. If you are in electronics, you are moving in this circle. Whatever you do, you are just moving in this circle. Okay, because unless you're doing digital electronics, otherwise as long as you're doing analog electronics, you're just moving around this circle. So what that means is that then on this unit circle, if you have some angle, like for example this angle over here, if you have some angle like this angle would be theta, for example 30 degrees or 20 degrees or 40 degrees or something like that. So if this is, for example 30 degrees, this would be 0 degrees. You can have different units for these angles. For example, you can use degrees, you can use radians, and you can use some other thing which is I'm not very much familiar with, gradient or something like that, which is usually not used by anyone. So, but I'm using degrees here, so 0 degrees, and then this would be, for example, over here 90 degrees, this would be 180 degrees, this would be 270 degrees, and this would be 270 plus 90 is equal to 270 plus 90 is equal to 360 degrees. 360 degrees, so 360 degrees would be one full revolution around this circle. Okay, and then this same triangle, imagine that the same triangle, this angle is moved over here, and now this is this side over here, now this is this side over here, and this is this side over here. This side has been moved over here, this side has been moved over here, and this angle is this angle over here, right? So we said that the sine of some angle is equal to the opposite by hypotenuse, so the opposite is this side and the hypotenuse is this side. Now in this circle, the hypotenuse, the length of the hypotenuse is always 1, because this is the radius of this circle, and all around the circle the radius is 1. So then in this circle, in this particular circle, the sine of theta is equal to the opposite side divided by 1. So I just don't have to write it. So the opposite side. So the opposite side would be this vertical length over here. This vertical length would be the value of the sine of this angle. And then the cos of theta would be adjacent to hypotenuse, but the adjacent over here is this length to hypotenuse, which is 1. So I can simply write adjacent. And adjacent is just this length over here. So this would be the length of the cos of this angle, which is the adjacent side of this angle. Okay. And now suppose that this angle comes down here. Suppose that this angle comes down here, and if it comes down here, that becomes a 0-degree angle, or the 360. But I want to start from 0 and then go all the way to 360. So suppose that I have a 0-degree angle. So then the sine of this angle. So if this is theta and this is the sine of theta, if theta is equal to 0 degrees over here, you can see that you have this angle over here, and this vertical length is 0. So sine of 0 is 0. If you come over here for 90 degrees, you can see that the length of this vertical length becomes 1. So sine of 90 degrees is 1. Come over here, which is 180 degrees, and the sine of 180 degrees again becomes 0, because there is no vertical length here. There is only this horizontal length. So that's 0. 270 degrees, you come all the way up to here, and you have this negative vertical length, which is -1. So 270 degrees would be -1, and 360 degrees is the same as 0, so it's 0, right? So this is the value of the sine function for these 5 main angles: 0, 90, 180, 270, and 360. Now, we can have the same thing for the cos function. So if you have theta and cos theta, so the cos function over here, if you have a 0-degree angle, you have this full length along the side, which is a horizontal 1. So the sine of 0 is equal to 1. I'm sorry, the cos of 0 is equal to 1. If you go to 90 degrees, this horizontal, basically there is no horizontal length over here, so the cos of 90 degrees would be equal to the cos of 90 degrees would be equal to 0. 180 degrees, you would have some angle over here, and the length of that is -1. The horizontal length is -1. And 270 degrees, the cos would be 0, because you have no horizontal length over here. So it's 0, and 360 degrees is the same as 0, which is equal to 1. Now if you draw a graph for this function, for these two functions actually, what you would get is that, let's say that this is the output of the function. Let's say that you see that the output is oscillating between 0, 1, -1, 0, 1, -1. So this is 0, this is +1, and I take this as -1. And then the inputs are here theta, and 0, 90, 180, 270, and 360. So you can write this as, in radians, you can write this as 0, and this would be 90 degrees would be pi by 2, and 180 degrees would be pi. 270 degrees would be 3 pi by 2, and 360 degrees would be 2 pi. And I'm not going to get into why basically why, for example, 90 degrees is pi by 2. It's a definition basically, and these are in radians, so that's 2 pi radians is pi by 2 radians, pi radians, and 3 pi by 2 radians. These are all definitions. So, but you need to, of course, you need to understand why, basically, because pi is used in many different ways in mathematics, so you don't want to confuse yourself. But it's not, I mean, that would make this video way too long, so I'm not going to talk about that right now. So I start from 0, and then pi by 2 over here, and then pi over here, and then 3 pi by 2, and then 2 pi, and then 2 pi. And then also I might need actually negative pi by 2, which is basically normally you move in this counterclockwise direction around this circle for positive angles. For negative angles you move in the other direction, and for example, if you come basically pi by 2 radians in this direction, this angle would be negative pi by 2, which is the same thing as 3 pi by 2. So that is negative pi by 2 means that you are moving around the circle in a clockwise direction by basically pi by 2 radians, and then you would get over here, right? So what that means is that you can start with the sine function. You can see that the sine of 0 is equal to 0, so that would be this point over here. Sine, basically this is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi. So sine of pi by 2 is equal to 1, over this point over here. Sine of pi is equal to 0, over this point over here. Sine of 3 pi by 2 is negative 1, so this point over here. Sine of 2 pi is equal to 0, this point over here. And sine of negative pi by 2 is the same thing as sine of 3 pi by 2, which is equal to negative 1. So you would have this point over here. So then if you actually connect these points together, you would get a normal, the familiar sine function with all of its beauty. This is the familiar sine function. Okay. So this is a sine function, and you can see that the sine function goes actually through the origin, and then at pi by 2 you are at the peak. At pi you go back to 0. At 3 pi by 2 you're at negative 1, and at 2 pi you're back to 0. So that's a periodic cyclic function that just keeps doing the same thing. Now I think I want to finish this one, and then I think this video is going to have also a part 2 that we will get to the actual calculations related to this experiment. But let me finish this thing, and then we will go back to the oscilloscope screen and then make a couple of measurements there. So now for the cos function, 0 is 1. The output at 0 is 1. At 90 degrees or pi by 2 you're at 0. At 180 degrees you're at pi you're at negative 1. You're over here. At 270 or 3 pi by 2 you're at 0. At 360 you're at 1, or 2 pi you're at 1. So you're over here. Okay. And at negative pi by 2, which is 3 pi by 2, you're at 370, which is 0. So that's over here. Okay. So that's the cos function. That's actually the cos function over here. Okay, so that is the cos function. Okay, so this function over here is f of x, for example, is equal to cos x, and this function over here is f of x is equal to sine x. Now I did all of this in order to show you that in order to show you the phase difference in between these two functions. So you see that if I think of this axis, this horizontal axis, as time, you see that this function, if you compare these two peaks, these two peaks over here, for example, you see that this function, the value of this function goes to this peak pi by 2 radians or pi by 2 units, whatever your units are, doesn't matter, pi by 2 units faster than this function. This function does the same thing after pi by 2 units. That means that this function, which is the cos function, is leading. We say that the cos function, the cos function leads, basically, this word is important, leads the sine function, by pi by 2 units. Okay, so we say that the cos function leads the sine function by pi by 2 units. Or another way of doing this, of saying the same thing, is the sine function, the sine function lags the cos function, by pi by 2 units. Okay, that's basically. So right now, if you compare these two functions, this is the cos function, this is the sine function. The cos function is leading and the sine function is lagging. Lagging meaning that when the function is leading, that means that it comes first, and when another signal is lagging, that means that signal is coming second or after that signal, if you compare. But it's provided that you compare basically comparable points on the two functions, meaning that, for example, you cannot compare this point on this function to this point on this function. They are not the same outputs. These two are the same outputs and you can compare them, right? So now I'm going to actually go to the oscilloscope screen and take a look at our signals over here, and basically see what we have over there, see how much leads or lagging and so on and so forth we have over there, and then we will see about the rest of the story. So let me see. Okay, so now you see on the oscilloscope screen that we have here, what happens is that these two signals over here, this is my output signal and this is my input signal. So if you go over here, and if you compare the two signals, you see that the output signal is actually leading the input signal. The output signal, which is this one, which is moving, is actually leading the input signal. And how you can tell that? You see that this is this point over here. You see, if you take a look at the peak of this peak over here, this peak is actually leading the other peak, which is related to the input. But it's not easy to compare the peaks. So what you want to do is you want to pick a center line for example, let me see, this is my input actually. So you want to pick a center line for example, for your input. The center line I'm going to pick over this line over here, which has all of these graduations on it as well, so that I can actually use those graduations in order to read something here. So I'm going to ground channel 1 so that the output goes to 0, and then I'm going to, you see, you can actually adjust this line to be just on that center line, right? And once you're on center line, you can unground it, and now your signal is centered around that horizontal line. That's what you want to do with the second signal as well. So I move the second signal over here and I ground it, and now I can center it just around that line, and unground it. And you can see that over here I can compare these 2 points. For example, this point related to the output signal, this point related to the input signal, and you can see that the difference, or the phase difference between these two, is just about 1.5, around 0.15, actually 0.15 horizontal units, meaning that you see over here you need to oops, I messed it up. You see centered, okay. You see over here what happens is that this input signal over here is, if I move it around horizontally, I can move it over here so that for example this point is just on this crossing over here, so that I can read something on it, okay. And if I start from here and come all the way down here and up here, this is half a cycle, and then if I come all the way up to here, this is 1 full cycle. So you see on this signal 1 full cycle is happening on 1.2, 0.4, 0.6, 0.8, and 0.9 horizontal units. So 1.9 horizontal units is 1.9 horizontal units is actually 360 degrees, or 2 pi radians, meaning that 1 complete cycle, because the period of a sinusoidal function like a sine wave is 2 pi radians. So half of the cycle is happening in like 0.2, 0.4, 0.6, 0.8, and 0.95 horizontal units. 0.95 horizontal units is half a cycle. Okay. So that means that let me see, half a cycle is happening in 0.95 horizontal units. That's half a cycle is actually 180 degrees, right? Half a cycle. So what that means is that, so now I know that half a cycle over here means, or 180 degrees is actually on this scale is 0.95 horizontal units. Now I can move this signal up here and actually center it around this line. And unground it, and then you can see that the difference between these two, for example, if you compare these two, this is, the difference is something about, if you move them, and then you can play with your time base to be able to read that better. But of course you would mess with your reading. Of course you have to, if you change this, then of course the scale that we talked about is going to change as well. So I'm going to do the reading anyway. So if you compare these 2 points, it's going to be each graduation is 0.2, so 0.2, and let's say that this is I don't know, 1/2 of 0.2, so 0.1, so the difference is 0.3 horizontal units. 0.3. Okay, not very, I mean, actually I should have, what I should have done is that I should have, I should have basically done this, meaning that I should have zoomed in horizontally more on my signal so that I could read my signals better. And now you can see that you can see that I have, for example, move this down here, and to do a better reading I'm going to, so now you can see that this is half a cycle, so this is half a cycle over here, right? And this is a full cycle. So half a cycle is happening is 2.3 horizontal units. So that means that 2.3 horizontal units is 180 degrees, half a cycle. And now I move the other wave up here, round it, center it around this line, unground it, and excuse the oscilloscope, this button is not very sensitive, I mean it's overly sensitive. So now the difference, if you, for example, compare these 2 points, you can move them around horizontally this way, and you can see that you can play with the intensity and focus as well, so you can get a good reading. And you can see that the difference is 0.2, 0.4, 0.6, 0.7, 0.7 horizontal units. Okay, good. So now comes the calculation with this. I didn't actually want this video to be so long, but there is no other way. Okay, so what we said was that based on the reading that we made, 2.3 horizontal units was equal to 180 degrees. And the phase difference was 0.7 horizontal units, and that corresponds to how many degrees? That's going to, x is going to be equal to 0.7 times 180 degrees divided by 2.3, and that's equal to 0.7 times 180 degrees divided by 2.3, which is equal to 54 degrees. Okay, it's equal to 54 degrees. 54 degrees. So I know that the output leads the input by 54 degrees, if I'm not wrong. 54 degrees. 54 degrees. So that's basically all that we need basically in this experiment with this RC circuit. In the next video we will use these findings that we found in the experiment to do some calculations and see basically how we can actually calculate these these values using mathematical expressions and some formula. So I'll see you in the next video. Thank you.